So the topic today is chemical energetics. And now let me just quickly go over the concept that we have from O levels. We know that there are two kinds of reactions, the exothermic and the endothermic. We know that in both of them, there is transfer of heat energy. And there are two things. There is a system, which we will consider to be anything that's taking part in the reaction. So system is what takes part in the reactions. For example, we have a simple reaction, magnesium reacting with sulfuric acid. Now, in this case, right now, this is solid, this is aqueous. So your system will be water, which is your solvent, the air around it, the volume of whatever you have, the test tube, whatever you have thermometer probably in there, you have magnesium, you have sulfuric acid, the moles of sulfuric acid, the particles of sulfuric acid. You may be yourself obviously involved in doing this experiment. So out of that, are there things that you cannot consider part of the system? So this is the beaker in which we are doing this experiment. This is sulfuric acid solution. I put some magnesium in there. There's the thermometer and I leave it open, okay? Now, and you are doing the experiment. So out of all of this, who is part of the system and who is not? So is the magnesium part of the system? Again, system is what takes part in the reaction. System is without which the reaction cannot occur. So do you think this magnesium solid, these particles, they are part of the reaction? Oh,
Yes,
sorry, I mean part of the system. Yeah, they are. Obviously, they're part of the reaction. What about this solution? Water in there. Is that part of the system?
Sir.
Why not?
Sir, I don't know. It just doesn't feel like part of it.
It's not actually, because right now, the only thing that is part of the system are these two things. Water is not the solvent. All it's doing is separating the particles away from each other. They're not part of the system. The air around it, not part of the system. The beaker, the thermometer, the person doing it, not part of the system. The only two things that are part of the system are sulfuric acid molecules or ions, because this will ionize obviously, and magnesium solid. That's it, nothing more, nothing less. Now, in this system, everything else around it, the solution, the solvent in there, the thermometer, the beaker, the person doing it, the environment, that is surroundings. And system can give energy to the surrounding or take energy from the surrounding to complete the reaction. So during the completion of this reaction, there's going to be some energy exchange, some heat exchange, transfer of heat energy. And that can be from one direction to another. And depending on overall amount, so it is possible and you will get some energy flowing from surrounding to the system first, and then system will give back some energy to the surroundings. And then the overall exchange, the net change in energy that you get will decide if the reaction is exothermic or if the reaction is endothermic. Now, we are going to talk about all the energy changes from the perspective of the system. So we are going to consider magnesium particles, sulfuric acid particles, whenever we consider how much energy is coming in or going out. So when I say energy has increased, I'm basically saying that energy of the system has increased. And that means surroundings have provided energy to the system. Magnesium and sulfuric acid particles have gained energy. When I say energy has decreased, then magnesium and sulfuric acid have lost energy and the energy has gone to the surrounding. It could be the beaker heating up, it could be thermometer absorbing and showing it on the thermometer, of course, or it could be somebody touching the beaker, unfortunately, and burning their hands or something. So all of that is how the energy change happens. And depending on the overall change in energy, this is endothermic or exothermic. So we know it from O levels. We also know that there are reactions in which there is more energy given to the system and less energy taken from the system. And we call them endothermic because overall energy has entered the system. So photosynthesis, it is where sunlight, which is the energy being given to the photosystems, light system 1, light system 2, all of that. And sure, there is some energy given out, but overall heat energy, the sunlight, is being absorbed. Similarly, when you eat something with menthol in it, or Trident mint flavor or something, it takes energy from your saliva, from your mouth, and it absorbs that. Obviously, some energy is also given out, but overall energy is being taken in. So that means it is endothermic process, decomposition, endothermic, all of that. Now, what's happening is system is getting more energy than it's giving out. So it's all about what is coming in and what's going out. So when it's going out from the system, we give it the negative sign. So system giving energy to the surrounding is negative, and system getting energy from the surrounding is positive. So when you have overall positive answer, which means energy is being taken in more and given out less, that is endothermic process. Now, imagine burning a fuel or a respiration process where and glucose is broken down and heat energy is released. Sure, breaking glucose requires some energy from the surrounding, which is basically your body, and glucose then leaves energy, gives energy out, and that is to the surrounding, which is again you, your body. But overall, more energy is given out than is absorbed in. So the negative sign takes precedence over there. Similarly, when you're dissolving something in water, for example, have you seen those calcium tablets? Uh, People have been recommending them for years that you should take one daily. Those calcium tablets, if you put them in, they leave this. There's a lot of bubbling and all that. So that is again a calcium salt that is dissolving in water. So it is possible. We'll have to see what the salt is. It is possible that that's also an exothermic process, and the water, the solution, is heated up a little bit. Sure. Now, there is a technique to figure out how much energy is taken in or given out, and that is called calorimetry. So, calorimetry is how you can measure what amount of energy is taken in or what amount of energy is given out, and you can exactly map out what the reaction is going to do in terms of energy. And that will give you what we call enthalpy. And enthalpy is delta H. It is the change in energy. Now, here's an interesting part. You can't measure. Experimentally, we have no method of measuring the energy of the system at any point. We can't. But what we can do is measure this change. So we can measure how much is taken in, how much is given out. We can measure that. We cannot measure the energy of surrounding individually. We cannot measure the energy of system individually, but we can measure the change. And based on that change, we give the reaction its name: endothermic, exothermic. Now, there is the reaction pathway diagram, which we have seen before. So for example, if you were burning methane, this is the energy profile diagram that you will see. So we are all familiar with this from O levels. Let me just quickly see what's happening. So over here, our system started with methane and oxygen gas, and they're the reactants. Now, any chemical reaction starts with the reactants changing to products. It can be reversible or it can't be reversible depending on the energy requirements and multiple other factors. Now, you will always see a hump in this energy profile diagram, regardless of what reaction you're looking at. You might look at a reaction that is different from this. For example, if I had calcium carbonate and I was breaking it down, it will give me something like this probably. Now, there is again a hump in there. This hump basically tells me that, sorry, excuse me. So this hump is basically telling me that this increase in the system from here or from here, the yellow part, that is always before any products are made. Reaction must always absorb energy. The system must always get energy from the surroundings. And what does that do? That obviously raises the energy of the system. So for the reaction on the left side, this highlighted in blue part, that's your system. So when it gets energy from the surrounding, its energy increases. And we have already established that when system gets energy, that is positive. So as you can see over here, the energy is increasing. It's a positive change. Similarly, on this side, calcium carbonate, this thing in blue, that's our system. So it's getting more energy from the surroundings, and this is giving it a positive change. So that is why there's an increase in energy. Now there is this orange part here where the energy is being lost, or you can see a negative change in overall energy of the system. So the system overall is losing energy. This point over here, this is what we call a transition state. This point over here. This transition state is the maximum energy for the system. It is where the system has the highest energy. Now, this black arrow, if you can see this, labeled EA, that is the minimum energy required for the reaction to occur. And this we call activation energy. So that black arrow, that is your activation energy. And this is the first important definition that we have. Activation energy is the minimum energy required for the reaction to occur, or for the reactants to change to products. Now, this varies. The amount depends on the reactants or the system. Now, there's also the red arrow. This red arrow is your enthalpy, and that's your second important definition. Enthalpy is the energy difference that you have. It is a difference in energy of the product. So I can call it the energy of the product or heat of the product minus the heat of the reactant. And if you look at the diagram, both of them, you will see that heat of the product is actually the final state of energy that the system has. And heat of the reactant is the initial state of energy that the system has. And you're simply subtracting final minus initial. That's it. So in any transaction, for example, I do a business, I start with $100 and I end with $200. So my change is 200 minus 100. In another day, I start with $100 and I have 75 at the end. So my final change is 75 minus 100. So as far as I'm concerned, the system, the business has lost 25 joules. And that is, sorry, $25. If you were to translate that same scenario to products or the system, then whatever energy the system has at the end is telling us the change that you have. So final minus initial, that is delta H, or enthalpy change of the system. So when you get a negative value, it simply means that overall the system has lost energy. Similarly, if you were doing a business, a negative value at the end would mean that you have incurred a loss because the business has lost money. In the case of system over here, a negative value means the system has lost energy. And the unit of energy over here is not just joules, because this is not exactly energy. This is enthalpy. And enthalpy is slightly different from energy in the way that enthalpy depends on the particles. So if you were to define what enthalpy is, it would be energy per particle or energy per unit particle. So let's figure out the units for this. So energy has the unit of joules, or if you have large values, we usually put them in kilojoules, where K is small and J is capital. And then you're dividing them by how many particles you have. You're dividing them equally. And particles, we measure them, the amount of particles is measured in moles. So the unit becomes kilojoules mole minus 1, or kilojoules per mole. And that's the unit of enthalpy. So that's how enthalpy is different from energy. So energy and enthalpy are related, but enthalpy is not exactly energy. It is energy per unit particles. Now, where is this energy being used, or where is it coming from? So there's the collision theory that we have already seen in O levels. Collision theory says that colliding particles, when they want to react, they must possess a certain amount of energy with which they collide with each other. Without that minimum energy, they will not end up with something else. So what's happening is that if you want them to react with each other, you have to give them a certain amount of energy with which they will collide and break up or make new products. So that's the first important point. So why do they need that energy? Because they need to collide with enough force that the bonds that they already have are broken. So they must collide with enough force that the bonds that they already have must break. So obviously that force you need to supply in the beginning. And that is why activation energy is always positive. It's always supplied from the surrounding to the system. All right, do you get it? Why is activation energy always positive? Do you all get it? Meher, what do you think? Why is this positive?
Sir, because it's coming from the surroundings into the system.
Sure, that tells us the direction of energy, and because the system is getting energy, it's positive. Sure, but why does it always come from the surrounding? Why can't in one reaction system produce it? What do you think? I don't know if you can hear me. So, what do you think? Why can't system produce this energy?
Sir, because there's like a limited amount of energy that the particles have at like that specific moment. Like they need to be supplied with more for like more collisions and stuff to occur.
Yeah, exactly. And another way to look at this is that if the system already had that energy, then it wouldn't be the system there. It would have already done the reaction. So if the system is there, like magnesium particles are mixed with sulfuric acid and they're not reacting, that means that they don't have energy that they need to react. So it must come from outside and they must get that energy to start doing the reaction. If they already had that, they would have reacted. So that wouldn't be the system we are working with. It's that simple. So if you look at the diagram, the yellow part is always energy absorbed. So you can say that this is always energy absorbed. And the orange part is always the energy released. Okay, regardless of what reaction you have. So that's a similarity in endothermic and exothermic reactions, that there's always an up arrow and there's always a down arrow. And it's simply a vector addition. So a vector upwards compared to the vector downwards, whatever the difference is in their values, tells us the overall enthalpy. Now, there must be a way for us to actually figure out what these arrows are, what their values are. And there is. For covalent compounds, we use a simple method called Hea's law or Hea's cycle. This Hea's cycle is based on two parts. So Hea's cycle tells me that if you want to know what the change in energy is or what the arrows are, then upward arrow is the bonds breaking and downward arrow is the bonds made. That's it. So just figure out the difference in bonds broken and the difference in bonds made, and there you have it. There you have the difference in energy, and that will give you the delta H. Now that is Hea's cycle, and we use it for covalent compounds. Now there's also a Born-Haber cycle. This Born is Max Born, who was I think he was a friend or colleague or a student of Einstein, and Haber, who was definitely a friend of Einstein. And Haber is the same Haber who gave us ammonia, the best method we have of producing ammonia, even after 100 years of that process. So Born-Haber process is used for ionic compounds. So Hea's cycle, usually we break it down into 3 stages. And there's the bond breaking, there's a bond made, and then finally the enthalpy change. And Born-Haber process, we usually break it down into 5 stages, which is for ionic compounds. So this is for usually covalent compounds, and that is for ionic compounds, but they're both built upon each other. In A1, we will look at Hea's cycle, and in A2, we will look at Born-Haber cycle, although they're both technically roughly the same. All right. Now, the next thing that I want to talk about may be a little repetitive, or something that we can like you just need to understand what it is, and we will apply it multiple times. So here's the thing. There is a standard that we have set. So standards are important because scientists from all over the world, they want to work together, they want to collaborate, and it's important for effective communication, for effective like to improve the efficiency of the whole process. So the standard are set by, there is actually a society for usually every different standard. There is a society, like for standard names of compounds, we have IUPAC, or for standard units, we have another uh, organization that has a headquarter in Paris. So we have these standards set. Now for chemical reactions or enthalpy changes, if you want to have a fair comparison of a scientist working in Pakistan compared to a scientist working in US or Australia, then for a fair comparison, we need standard conditions. There are three parts to what the standard conditions must be. Number one, the pressure should be 1 atmospheric pressure, which is 101 kilopascals. Okay. In some books, they have mentioned it as 100,000 pascals, but technically it is 1.06, I think 68 or something. So that makes it 1.01 into 10 power 5 or 101 kilopascals. That's the first thing we need. Second, we need a temperature of 25 degrees Celsius. And we have already discussed how to convert one unit to another. So because the standard unit for temperature is Kelvin, so we have 298 Kelvin. And again, this K is capital and that K is small. So it's important that when you're writing it in exam, your small k should look different from capital K. So if you have a kind of writing where it's difficult to discern, make sure that you start adapting this process. So 298 Kelvin, or that is equal to 25 degrees Celsius. If you want to convert, just add 273 to 25 degrees Celsius, and you have 298 Kelvin. And then the third part is that substances should be in their normal state. Now, what does a normal state mean? It means the state at room temperature. Because if you notice, 25 degrees Celsius is room temperature and 101 kilopascals is room pressure. So this part, we have already seen it as RTP, and this is the extra part, and substance must be in normal state. So what this means is that, for example, if you're burning methane, then you will get steam, right? But in a standard equation, we will mention it as liquid, because steam is not at 25 degrees Celsius. Steam does not exist there. Water exists as liquid at 25. So we must mention liquid for the state of H2O that you have. So these three things, they come together and it gives us the symbol of the standard equation. So this is a circle with a line through it. So kind of like Deathly Hallows, except for the cloak. So this is what you have, the standard condition symbol. So in any reaction, if you have this symbol, that means that this reaction was done at 101 kilopascals, 298 Kelvin, and every substance was brought back to its original state. So if you're doing a reaction and you want to measure the standard enthalpy change, then you must wait for steam to condense back to water. Carbon dioxide will remain gaseous. So here's the thing. If I were to do a reaction, let's suppose, again, burning of methane, I can write this as CH4 plus O2, making CO2 plus water. If I balance this, this gives me, yeah, this is balanced. Now, methane can be gaseous, oxygen can be gaseous, carbon dioxide can be gaseous, and steam can be produced. And in this case, I can just write delta H. I cannot write delta H with a standard symbol there, because unless I change this gas to liquid, it is not in its standard state. And now I can write this thing. And this is the standard enthalpy change. And obviously every reaction has a standard enthalpy change and we can measure. What am I saying here? I'm saying that this is the enthalpy change when 1 mole of methane reacts with 2 moles of oxygen gas completely to produce 1 mole of carbon dioxide and 2 moles of water. See, I said water, I did not say steam, because I'm talking about room temperature and pressure. So water has to be liquid and everything else is gaseous. So here's the thing, whenever you are writing equations, writing the state is super important, because the states must match the environmental state that you have, the temperature, the pressure. So it's really important that the state that you've written matches it. So now on, in any equation that you have, particularly an equation with enthalpy changes, make sure that you write the state symbols. And obviously, delta H, if it is at room temperature, it will be a circle through it. Now, there are a few processes which we use multiple times and we have given them their names. So there is a thing called formation. Now, the chemical formation of things is basically when something is made from its elements. Formation is the process of something being made from its elements. So that's super important. So if I would talk about carbon dioxide, then formation of carbon dioxide is carbon reacting with oxygen to produce carbon dioxide. Notice that carbon is just the carbon solid and oxygen is just the elemental oxygen. It's not ozone, it's not oxygen, atomic oxygen, it's elemental oxygen, which is O2. And this thing, we call it the delta H of formation. Now, right now, without writing the state symbols, I cannot say whether it's standard or not. So if I want it to be standard, I will mention that carbon is solid at room temperature. And this carbon is most likely graphite, or it must not be diamond, but it could be, sure. And oxygen is gaseous and carbon dioxide is gaseous, because at room temperature, these things are like that. Now, that is delta H F. Now, F means formation. Okay, so that's the first one that you have. Now, if I want it to be standard, then I must mention the definition to be standard as well. So what is the standard enthalpy change of formation? So formation is a product made from its elements. Now, if I want it to be standard enthalpy change of formation, then I must add something to the definition of formation. So I can't just say that it is a product made from its elements. I must mention that it is the enthalpy change when, and here comes the standard part, 1 mole of a product is made from its element under standard conditions. So the standard part is important. And what are standard conditions? Standard conditions are the two things in a room temperature. They are the 101 kilopascals and 298 Kelvin. And of course, the states will reflect their state at those conditions. So delta HF, if you want it to be standard, you must balance the equation in a way that you get only 1 mole of the thing. So let's say we have aluminum oxide. So I want to write the standard equation for aluminum oxide. So how will I do that? Aluminum oxide is this. Now I will look at the formula first and then look at what elements I need. So I need aluminum, I need oxygen. Okay, I've done that. Now I must balance it in a way that I get exactly 1 mole of the product. And the best way to do that, simply take the values. So for example, how much aluminum do you have on the left side? 2. How much aluminum on the left? How much aluminum on the right side? 2. On the left side, 1. So 2 over 1, that's 2. Now, how much oxygen on the left side? 3. How much oxygen on the left side? 2. So 3 over 2. Take a ratio, and that's it. You're done. And that's a pretty neat way of balancing an equation, regardless of whether it's formation or not. But in this case, it has actually helped us. Notice that the state symbols also reflect the conditions. So this is delta HF, and I can now put standard here. Now, if I had another one, so let me give you a compound. Yeah, go on, write down the equation for formation, standard enthalpy change of formation for sulfuric acid. Go on, sulfuric acid is H2SO4. So go on, complete this equation. Okay, done. Vamik, what's your equation? Can you say it out loud?
I'm not done. But can you repeat it once?
Yeah, so write down the standard enthalpy change of formation of sulfuric acid. We have hydrogen, sulfur, and oxygen. These are the 3 elements. So we write the elements. So H2, because hydrogen exists as H2. S, because it exists as S. Now here's the thing. Elemental sulfur does exist as S8. Sometimes we do get it in like S16 or S64 even. So to keep things simple, we just keep it S, unless it's mentioned that we are talking about S8. Okay. Similarly, oxygen exists as O2, so we write it as that. And now we just need to balance it out. So hydrogen is balanced, sulfur is balanced, oxygen is not. I have 4 oxygen on the right, 2 on the left. So 4 over 2, 2. So that's how I balance it. Now that's one part. Now I need to mention the states. So this is gaseous, this is solid, this is gaseous, this is solid. Sulfuric acid would be a solid at room temperature. So there you go. We usually need to dissolve it in water before we react. Don't write aqueous. So there you go. So this is delta H formation standard for this thing. Okay. Now here's the thing. HCl. Try to write this one.
So 1/2 H2 plus 1/2 chlorine with the diatomic.
Excellent. Yeah, exactly. Because they're diatomic, we need to put fraction in there. And we just need to make sure that we have 1 mole of HCl. That is something we cannot compromise on. The state symbols, what will those be?
So gas, and I'm not sure about HCl.
So HCl is also a gas at room temperature. So that is why it is delta HF. All right. So there you go. This is how the standard enthalpy change of formation is written or made. Now, you can also have another one, and that is again used a lot of times, which is standard enthalpy change, or the process is called combustion. So combustion, as you know, it is burning of something. Okay, so when something burns, this is the process in presence of oxygen, obviously. Now, complete combustion is a process where something burns completely, which means you have plenty of oxygen.
Sure.
You have, yeah.
How will we know the states of the products at room temperature?
Usually the ones that they give us are the ones that you're familiar with in AS. And sometimes if there's a new compound, they just give you the state for that thing. So for example, if they give you ammonium chloride and you're not sure if it is solid or not, one way you can figure it out is what kind of bonding it has. If it has ionic bonding, it's most likely going to be solid. And if it has covalent bonding, then most of the things are gaseous, but of course it varies. So for example, if they told you about octane, then you have no idea what the state of octane could be. It could be liquid, it could be solid or gas. So in that case, they will tell you what the condition state is. Okay.
Okay, sir.
Yeah. But just remember that carbon, when we use it, we usually use it in the graphite form. The standard carbon that we have at room temperature is the one that is graphite. All right. So standard enthalpy of combustion involves knowing that you are going for complete combustion. What's complete combustion? When you have excess oxygen, when you have plenty of oxygen, oxygen is not running out. It's not the limiting reactor. And secondly, enthalpy change of formation, combustion is, so the standard would be enthalpy change when, again, this is the standard part, 1 mole of a compound, of a substance, in fact, because it can't be an element, substance is burnt in excess oxygen. Either you mention that you have excess oxygen, or you say that it's burnt completely in presence of oxygen. All right. And then under standard condition, don't forget that part, because without that, you can't have standard enthalpy change. So while combustion can happen at other conditions, while combustion can happen for more than 1 mole, but if you want to have standard enthalpy change of combustion, then it's important that first of all, you burn 1 mole of the substance. That's the most important part for the standard part. Then oxygen must be in excess. And thirdly, you must have standard conditions. These 3 requirements are important for the standard enthalpy change of combustion. And we mention it using this symbol, delta HC. So C means combustion, just like formation was represented by F, and delta HC with the standard symbols there. All right. Now, again, remember that combustion we usually do with hydrocarbons and all that. So it's important to know that you have graphite if you're concerned with carbon. So now, if I had the same substances like any of these, if I were to burn them, I will need 1 mole of them to burn. So every balancing thing should make sure that you have 1 mole of that thing. So let's start with a simple example like methane. So methane is CH4. It burns in excess oxygen. And that's why we usually balance oxygen at the end. We get carbon dioxide, we get water. And why am I saying water, not steam? Because it's again standard. So it has to be liquid. So the states must represent that. And this is gas and this is gas. And I have 1 mole of methane. This is 2 of this and 2 of this, as we know already. So 1 mole of that. Go on, try to burn C4H10. Now write the enthalpy change, standard enthalpy change of combustion of these two.
सर प्रोडक्ट में सिर्फ कार्बन डाइऑक्साइड का 1 मोल होना चाहिए, वाटर के 2 हो सकते
No,
हैं?
no, no. Yeah, anything can have any number of moles, but the thing you're burning, that must be 1 mole.
Okay, sir.
Gases plus 5 moles of water, which
So just tell me what your numbers are.
then 1 CO2 and then 5 H2O.
5 H2O, but how come you have 1 CO2? You have C4 here. So 4 carbons will give me 4 carbon dioxide, and 10 water, 10 hydrogen will give me 5 water. And oxygen, I have 4 times 2, 8 here, and 5 times 1, 5 here. So the total is 13. So 13 oxygen on the right, 2 on the left. So my balancing would be 13 by 2. And that's it. This whole thing is extra. So that's my enthalpy change of combustion. Now, these two processes are super important for AS. There are many other kinds of enthalpy changes. There is another one, which is the standard enthalpy change of neutralization. And let me just write the equation for that. What does it mean? It means when you have 1 mole of H positive ions neutralized, but 1 mole of hydroxide ions. And that's it. You have 1 mole of hydrogen ions reacting with 1 mole hydroxide ions, producing exactly 1 mole of water. And that is your enthalpy change of neutralization. There's another called enthalpy change of atomization, where you break things down into their atoms. So for example, if I have calcium carbonate, now this will give me calcium atoms, carbon atoms, oxygen atoms. And all of these atoms must be separate from another. So that means they must all be gas. So whatever substance I have, I break it down, convert it to its atoms. That is called standard enthalpy change of atomization. There is also standard enthalpy change of ionization, which is what we have seen before. It is the ionization energy. And we have seen it before. So for example, if I said ionization energy 1, it means that you make a positive ion with power 1 here or a charge 1 here. So there are many kinds of enthalpy changes, but the most important ones in AS are combustion, formation. These are the two that we'll work with for now. Now, what if I don't have something that is either combustion or formation? If I have something like, if they ask me, okay, HCl is reacting with ammonia, producing NH4Cl. Now, sure, there is neutralization happening, but this is not water being made. So I can't say that this is neutralization. I can't say this is formation. Why is this not formation? Why is this not formation?
Sir, I don't know.
Anybody else?
Is it because the
Go on,
reactants are
Sarah.
compounds?
Yeah, exactly. For formation, the reactants must be elements. Okay, Laiba, are you clear with this?
Yes, sir.
Great. So reactant must be elements for something to be called formation. So this is not formation, this is not neutralization, this is not combustion because I don't have oxygen there. So what is this? This is simple good old delta H of reaction. That's it. R means reaction. It could be standard because the states are pretty standard, probably, unless they tell us, we can't say, but it looks like it is standard. All right, now tell me, is this enthalpy change of combustion?
No, sir.
Why not? Hydrogen is
Car-
burning in presence of oxygen, making water. Okay, how about now? Is this enthalpy change of combustion? It is. Hydrogen is burning with as much oxygen as it needs to make water. It is enthalpy change of combustion.
Sir, can you repeat the one above the
What do you mean?
HCl? Enthalpy changes that.
So that one is just enthalpy change of reaction. It's neither
Okay.
combustion nor formation nor neutralization. It's just reaction. Now, the second one, it is enthalpy change of combustion because you are burning hydrogen to make water. What it's not is standard enthalpy change of combustion. Because for standard enthalpy change of combustion, I must burn exactly 1 mole of hydrogen so that I get water. So I'll just balance this. And there you go. It is standard enthalpy change of combustion. Now, interestingly, this is enthalpy change of combustion of hydrogen, but this same equation also means the enthalpy change of formation of water because I am getting 1 mole of water. Same equation can represent multiple enthalpy changes and they will have the same values. And that is because of a very important law, which we'll discuss tomorrow. But for now, we are done with enthalpy changes for today. All right. See you tomorrow. Take care. Allah Hafiz.